All right, let's go ahead and get started. Welcome back. We are shifting focus one more time, where we've been talking about implementation practices and architectural practices for reuse-driven systems. And now we're going to shift once again into testing. As usual, please feel free to ask questions in the chat, and I'll take a look at those as I see them. So something we haven't talked about much at this point is testing. And today we're going to get into the testing of systems with a lot of variability, like software product lines, but not exclusively, but really systems in general, where you might have a lot of input and where you might make a lot of decisions when you execute or run those programs, and where those choices and those interactions can matter and influence each other's execution. Right, so today we're going to focus on testing at what we call the system level, which is through a defined interface, as opposed to unit testing where you test little bits of code like classes directly. At system level testing, we test through APIs, through user interfaces, through the command line, through any kind of interface to the system as a whole. And we'll introduce the process for how you create these system level test cases, where basically you identify the functionality that we can test independently. We identify for that the choices that we're going to make when we're testing, and then representative values for those choices. We, from there, combine those choices to create test cases and execute those against the system. So I know some of you have taken a testing class, right? But not all of you in all likelihood. So let's start here by laying down some basics and some terminology. Testing is the central activity of what we call the broader verification process of making sure the software works as we expected and is robust to failure. And testing is really our primary means of determining whether the software works correctly and whether it obeys all the different constraints we set on it. So software testing is fundamentally an activity, or an investigation rather, that we conduct to assess the quality of the system that we're developing. It's the search for deviations from some expected set of behaviors. Right? And testing is based on sequences of stimuli and observations. Essentially, we poke the system and we see what happens. We create a series of stimuli that the system has to react to, that we pass input to the system, or we create environmental conditions the system has to react to. Basically, we poke it and we see what it does, right? And from this, we record observations. We note how the system reacted to that stimuli. We mark down the output, the actions taken, the internal state of the system, even things like power consumption or bandwidth usage. Anything really that we can use to analyze the system behavior, and we use that to render verdicts on the correctness of the system. Right? Is it working as we expect, or is it not? So during testing, we take the system that we're developing, the system under test, and we run test cases against it. We instrument the system. So we prepare it in a way where we can monitor its behavior when it processes input, and we record information like the values of output, of functionality, of the current values stored in class variables, timestamps and when the system issues output or took actions, and a lot more. Right? Anything basically that you can use to check the results. You compare those observations against some pre-recorded embedded idea of what is correct. It's what we call the test oracle. If you write a unit test in JUnit, for example, you write assertion statements. Those are an oracle. Those embedded expectations of what the system should be doing. And then we issue our verdict. Pass if everything matched our expectations, and fail if it doesn't, if something is wrong. Now, the real limitation of testing, the real thing to keep in mind here is that testing can be used to show the presence of bugs, but it cannot provide evidence of their absence. Because you cannot test the system exhaustively, we can't possibly try everything, every single input. Any system of any reasonable size is going to have a near infinite number of input combinations. And so testing is really an optimization problem. Given our time, given our budget for testing, what's the best we can do? Can we make the system act up? what are the things that are going to increase our likelihood of that? Can we find those problems? Can we make enough of an argument that the system is good enough to deploy into the field? Right? No matter what, you'll never test everything, but you want to gather some evidence that you fixed the real problems, the things that are going to cause massive disruptions to your customer base. So to test a system, to conduct that investigation, you build test cases. And the two most important components of a test case are, first, the input, right? This can be method calls in a unit test. This could be requests to an API, like a post request to GET request to a REST API. This could be some kind of interaction with a user interface, like you touch the screen at certain coordinates, or you click and drag an element, right? But it's how you make the system react. The second is the test oracle, how we check the correctness of those observations that we take in the system. Some way to tell if what you observed was the right behavior. To know that there's a problem, you need to know what good behavior looks like, and that's the role of the oracle, is to embed your expectations on correctness. These come in many different forms, but I mentioned before assertions are probably the most common version of this. Now, when building a test case, there's also three other things you tend to include beyond the inputs in the oracle. You have any initialization steps to set up the system to put it into the correct state to start running the test case, right? That might include logging in. That might include setting some initial values to make the system ready to run your test case, whatever you need to do ahead of time. You have your actual test steps. This is basically how we apply the input, right? It's the series of actions we're going to take to apply that input and make the system to do something, as well as any code we write to prepare to use that oracle to compare the expected results and the actual results. And then when you're done, you have teardown, anything you need to do after this test is done running to prepare for running the next test case, to make sure that all of your test cases are independent of each other. Maybe that's logging out of a system. Maybe that's disconnecting from a database or switching users, something like that. Anything that you have to do to get ready to run that next test case. Now, we can break testing into a series of independent stages that we stagger throughout the development process. And these stages are largely built around different levels of granularity within the system under test. So if we look at the system from the outside, it looks like this box. It has interfaces, right? Maybe a GUI, maybe an API, maybe some kind of command line interface, and so on. Any way we have of interacting with this system. Right? However, there's a lot going on inside the system as well. The system as a whole tends to be architected, as you saw, as a set of larger independent subsystems, right? Each of those subsystems has their own interfaces, usually at least some kind of internal API, at least a class sitting there with a series of methods you can call. And those subsystems communicate with each other through those interfaces, right? And then within those subsystems, we have a bunch of individual standalone units, individual classes, all working together to produce the functionality offered by that subsystem by calling the methods and other classes when needed. And with those methods forming another kind of interface, where each class has its own interface, by that being the set of methods it defines. Now, we need to test at all of these levels, at the class or unit level, at the subsystem integration level, and at the system level as a whole. Okay. So broadly, when we talk about testing, we talk about either unit testing or system level testing, with a couple of distinct types of testing in there. And then there's other things too, like usability or user-focused or acceptance testing. But really, we're talking about running input against the system and seeing what it does. We're talking about unit testing, and then various levels of system testing, again, with some distinctions. All right. Unit testing is where we spend most of our testing time, and that's just the basic question of what are the methods of a particular class work. All right. We take small pieces of the system, the smallest chunk of the system that we can work with in isolation from everything else. Usually, like I said, a single class or maybe a small cluster of classes, and we test it on its own. We come up with tests for each of its methods. We try to isolate these units as much as possible, even faking the results passed from pieces of the system we aren't currently testing, what the process called mocking. And then we move up the ladder to what we collectively call system testing, which encompasses really three things, right? What we call subsystem integration testing. We bring those units together, which have now been tested independently, and we test their integration with each other. Can they now work together without breaking everything? Even if we've tested the individual units, faults can emerge from their combination, and so we need to bring those units together and test their combination and whether the subsystem as a whole can perform the functions that we stated in our specification, right? And then we move up again, and we can test the system as a whole to ensure that there aren't any integration errors between the subsystems and that the product as a whole meets all of the requirements we set on it. This is called system integration testing, right? And then the third element of system testing is what we call UI testing, where we test from the direct perspective of a user, generally through a GUI or some external API. But even though system integration testing kind of handles that, but often here the focus is from the user perspective. And does the user's interactions with the system work as we would expect? System integration testing, UI testing have a blurry line between them, right? It more comes down to whether tests are run through the GUI and UI testing, or a program level interface like a REST API or through the command line, and that's more of the system integration testing level. Now, if you have taken a testing class, you've probably focused heavily on unit testing. And that makes sense because that's the bulk of your testing effort. So in the land of software product lines or other reuse-driven systems, we're more focused on the system level, but it's still worth setting the stage a little bit by talking a little about unit testing and work our way upwards, right? So as I said, unit testing is the process of testing the smallest isolated unit that can be tested. Often a class and its methods are a small set of dependent classes that can't be separated out. And there's a big emphasis here on isolation. Classes are often tightly interconnected. And when a problem occurs, it can be really hard to figure out who's at fault. Is it this class that you're calling or some other class it depends on? And it gets harder to isolate issues the more dependencies you have. So it's in your interest to try to test these units as alone as you can. And so one thing you often do is you fake the results of method calls to other classes, and that's called mocking, where you return a preset value instead of actually calling another class. The test input for unit tests is usually calls to the methods of that class with different input parameters. And our oracle is usually a set of assertions on either method output or the class variables, where we check, well, does it have this value that we expect? Or meet generic properties we'd expect. That we then check the state of those, compare those to our expectations, and return the test verdict. So if you're writing unit tests for classes, your test should generally test all the different jobs, the responsibilities associated with that unit. In general, at least call every method offered by that class once, and then maybe try it in different configurations. If the methods are meant to interact with each other, make sure that you call the right sequence of those methods in different orders even, just to make sure that everything works as you'd expect, right? When you do this, you want to set and check the value of all the class variables as well, right? If there's class level variables, look at the ways that those variables change in response to method calls and try and manipulate those in the way that can break the system. Call those methods and try to corrupt the value of the class variables and put those variables into different broad states, broad types of values based on the kind of outcomes we'd expect from how those influence the result of the methods we can call. Right, so just a dead simple example, we might have a class called a weather station. It connects to a sensor unit in the field that gives us weather information. It has a few class variables. As an identifier, it has the current temperature and it has the current atmospheric pressure. And then it has a set of public methods that we can call and work with. Right, it can check the link to the home base. It can report the current weather. It can report the status of certain instruments. It can restart the instrument. It can shut down the instrument. And it can reconfigure the instrument based on the set of commands that you send to it. And so when we're writing unit tests for this class, there's a few things we want to do. Well, we want to set and check the class variables. So look at how the methods interact with the identifier, temperature, and pressure variables, and try and manipulate those in such a way that you can get a bad result, get the wrong value for them. Manipulate those in some way that can cause another method to fail. You might want to also then look at the different jobs that can be performed by that class, right? Check its link to the home base. Try to restart or shut down or reconfigure instruments. Do this in different sequences and orderings too to see if we can break something as a result. And in general, remember to try and hit every outcome of the different jobs that that class can perform, right? Not just the good, happy path where it works as we'd expect, but look at different error handling scenarios. Look at exception handling in there and see if you can trigger an exception to make sure it's handled properly. Try input that triggers these error handling conditions and see that they actually do work as you would plan. And look at different possible return values of every method as well, right? Not every possible concrete return, but different types of returns that they can have. If there's if statements, for example, that can give you different return points. So when we're writing a unit test, we usually do this as a block of code, right? And this code is included in its own package within your project that can be executed and perform the series of steps we talked about. Setting up the class, executing input, checking the results with your oracle, your assertions, and cleaning up. Most languages have toolkits for writing tests. In Java, the most popular is called JUnit. And IDEs like IntelliJ or Eclipse have support for JUnit very well integrated into development environments, so you can write and run test cases within your IDE. Writing tests in JUnit, if you have not done this, and I hope, those of you who have taken the testing class certainly have. I kind of hope you have otherwise, but if you haven't, we'll just talk about this a little bit. Writing tests in JUnit is essentially as easy as writing a little bit more Java code. You just need to learn a bit of special syntax. And so what you'd usually do is choose some target, some unit from your code base, your class or a small group of classes, and then in a test package, write a testing class, which contains a series of unit tests centered around testing that target. Each test is marked with this annotation called @test. And so just as an example, we have a simple calculator class here, right? And this has an evaluate method that takes in a string that's supposed to be some kind of expression. It's going to split it around plus signs and then add every element of it together. So it's basically just performing simple addition, taking in a string. And we want to test this, right? So what we would do is we would create a testing class. In JUnit, each test is marked with this @test keyword. They're usually named with the word test, followed by some kind of context for why you're performing that test, a description of what you're testing and in what context it's performed within. So at a higher level, this might be what feature you're testing, but within a single class, it might be a method you're calling, as well as just some information about what kind of outcome we might expect or what kind of context we're testing in. And so that might be like the happy path should have good input, or maybe this is something where we're going to try and pass in null input and see what happens, and we just refer to it maybe as null input here in the name, right? You are then generally going to define inputs, try to run the function with those inputs, and then examine the output. There's a special call called fail that will declare the test a failure if you reach this point. So for instance, if an exception is thrown in this particular case, it'll fail because you expected none to happen. You can pass in an error message to that. You can pass in all sorts of information, but it's going to print this error message when it fails. You can compare the expected and actual output through if statements and issue fail commands if they don't match up, or you can make assertions about the results and declare properties that the results have to follow. If an assertion fails, then the test fails, right? So back to our calculator example, right? We have this calculator code we want to test that's going to attempt to perform addition based on the string you pass in. It splits that expression based on the plus sign, and for each substring, it converts it to an int and adds the value to the sum, returning that at the end, right? So we can write a test class for this using JUnit. When we do so, we can create classes for testing either a particular class or unit in your system, or for some other level of functionality at a higher level of the system level even. And you can use JUnit to write system level tests too, not just unit tests. Right? It's a generic framework, but it's generally used for unit testing. The convention is to name it after the class you're testing or the functionality you're testing, followed by the word test. And then you'd have your test cases each marked with @test, right? And within this, we have our initialization. We're going to create a calculator class. We have our test steps where we're going to call the method with some input. Our input is a string 1 + 2 + 3. We're going to check the result. We have an assertion that asserts whether the two things you enter are the same. And so we pass in 6 in the sum, and we say it should be the sum we get back, the expectation, or the actual result should be the same as our expected result of 6. And then we have some teardown where we declare this null. And like this is a kind of a dumb little example. You often wouldn't have this particular thing, but you might use the teardown to do things like log out of a system or flush a database, things like that. Right. That gives you an idea of what these test cases look like. So that's the gist. That's your 10-second introduction to unit testing. And now we can move the hierarchy a little bit to integration testing and system level testing. So most software works by combining multiple interacting units within multiple interacting subsystems within the overall architecture. And then when the individual subsystems work in isolation, we bring those together again, and we test the integration of those subsystems as the complete system. So functionality performed across units, across subsystems, or the system as a whole, is tested through a interface. Right? So our tests tend to be through either the interface of a subsystem, some sort of internal API within your system, or the interface level of the system as a whole through its APIs, through its command line interfaces, through its user-facing interfaces. And integration testing focuses on showing that functionality access through this interface behaves according to your requirements, according to your specifications and what the correct system behavior is. Interfaces come in many different forms, right? As I've mentioned, at lower levels, you might be talking about method calls. It's not uncommon that you section off parts of your code by creating classes that handle interactions within this. We talked about this in design patterns with the facade pattern, which defines an interface over a lower level series of classes. This might be some sort of actual API. If we're integrating different microservices together, each of those is going to have its own API layer, right? It's not uncommon at all to interact with not just your own microservices, but external microservices. For instance, if you're writing a web app, right? You don't usually do your own authentication. You do this through things like OAuth, right? And that's a microservice that has an API that you integrate with. And you integrate it into your system, right? You might interact through different REST APIs, through different message passing interfaces, and different command line interfaces and so on, right? There's all sorts of ways we can interact with a system. But we have some kind of interface that defines certain high-level functions that we can interact with. And within that, it's going to bring together different elements of the system to perform those functionalities. Right? So for example, we might have a subsystem made up of classes A, B, and C, and we perform unit testing on A, B, and C, and they're working quite well. But now we have to bring those together to perform the functionality of that subsystem. And so we want to apply test cases not to the classes, but to the interface of the subsystem they form. And errors in their combined behavior in the interface that those combined objects form are not caught by unit testing, because they only really emerge when you combine those objects together, when they're not tested on their own, when they're not tested with mocking, but when you actually bring them together and when they interact at runtime. Interface errors are one of the more common types of error in a complex system. These usually fall into 3 types. The first is just simple misuse of an interface. The calling component calls some other element of your system, and makes an error in the use of its interface and in how it's called. It just calls it in the wrong way. This could be that you passed in data of the wrong type or malformed data of some kind. It could be that you passed parameters or data in the wrong order. It could be that you passed in the wrong number of parameters and called the wrong version of a method, right? You could have an interface misunderstanding. So you, rather than something where you called it with bad data or called it in the wrong way, you might have just made bad assumptions about it. And as a result, the behavior returned from the called component was not necessarily what you expected. You got the wrong outcome. For example, a binary search. A binary search assumes that you fed in a sorted array. And so if you send an unsorted array to a binary search, it's not going to give you the right answer. It's a misunderstanding of its functionality, right? It's not going to crash, but it's not going to give you the right answer either. You also can have timing errors, and it's easy to forget about these, right? In timing errors, you have things like the producer of a data and the consumer of the data operating at different speeds is an example of this. And so one element of your system goes in to read some shared data resource before the element that it was supposed to write to it can get in there and write its changes. And so you get expired data, you get data that's no longer relevant. Right. And so you need to watch out for all three types of these interface errors and write tests to try and account for them and catch them. These testing types are not necessarily equal in the number of tests you write or the amount of effort you put in. Unit tests are usually the bulk of your testing effort. These are usually about 70% of the tests you write in a project. There's a rough rule of thumb, right? It's not always exactly 70%. It might be more, it might be less, but it's generally about 70% of your tests in the project. It's important to verify the class's work is expected before we start combining them. And it's really important to make sure that each little piece of functionality works as we'd expect, right? Then you move up to your integration tests, which validate either interactions between levels of the stack within a subsystem, right? It might be a cluster of classes, it might be interactions between related subsystems at the system level. And those tend to be about 20% of your test cases. And then finally, you have your UI test or your end-to-end test cases, which validate your user's journey through the system, which usually spans multiple subsystems of your app that you're writing. And those tend to make up the remaining 10% or so of your testing effort. That 70-20-10 split is what Google recommends for Android development, but that's a pretty good rule of thumb in general. It has a nice logical underpinning. The reason for this recommendation is that as you work up this pyramid from small unit tests to large complex UI tests, every test is going to increase in fidelity. It's also going to increase in the execution time and the complexity of the creation, the maintenance, and debugging of those test cases. And so you write a lot more unit tests than integration tests because those are simple and quick to execute, right? And they'll do a lot of the job of making sure the system works, right? And then you move up to these more complex test cases that bring the units together. Unit tests run through the command line, right, or through your IDE. On the machine you're using to develop your program, they run quickly in milliseconds. UI tests require running the full system. If you're working with something like Android, for example, you also then need to work through an emulator or a physical device. And then even then you should run your UI test often on multiple devices too. Even if it's a desktop or a web app, you want to run in different browsers, you want to run in different hardware configurations, often just to make sure everything works as you'd expect in different hardware, OS, and software configurations. And that's going to dramatically increase the required execution time. UI tests are also often fairly complex as they require as a result more maintenance effort too. The good news is that the split also works out even without the speed factor. Units are tested in isolation. Well-tested units will integrate more cleanly. If there are issues, those are usually due to the integration itself and not a problem solely in one unit, and you can diagnose and fix that. Creating more unit tests makes integration testing easier as well, which will in turn make your full-blown UI end-to-end testing easier as well. Right. So how do we write integration and UI tests? Here it's very dependent on the technology you're using. What language are you working with? What product domain, what interface type? But to give some simple examples, if you are writing Android apps, your testing is, your integration and UI tests can be done through just JUnit still, right? Where, for example, you have Android X, which allows integration testing, and the Espresso library, which lets you use JUnit tests to perform actions on the graphical user interface. If it's a REST API, you often test using Postman, right? Or if we were working with a JavaScript app, you often test through Postman. If it's testing a web app through the GUI, you often use things like Selenium to automate execution through the browser. Right? So we're not going to go through every possible testing framework out there, but a lot of these tests you actually will see will look very similar, right? So here's an Android UI test that uses the Espresso library to interact with the graphical user interface through a JUnit test case, right? We use this activity scenario API to launch a login activity, which is going to be where the user logs into the app. That's going to create this activity and bring it to the resume state where it's visible to the user and ready for input. We're going to synchronize with the OS a little bit, and we'll use this Espresso view interaction library to enter text into a couple of text fields and click a button, right? So what we're going to do here is we're going to type test user into the username field. We're going to type correct password into the password field. We'll then click the button, this ID button, and then we'll assert that we get the result back we wanted. And what we wanted was then to successfully log in and end up in this home activity, which is if you haven't done Android development, activities are just sections of your app, right? So this should launch, successfully log in, and then launch this home page, right? And here we use an assertion again, just like we do with unit tests of simple Java code. But here we're interacting with a user interface. So you see the same basic elements here, right? We have a setup where we launch the login activity. We have test steps and input where we type things into boxes and click a button. And then we have our test oracle where we assert certain outcomes that should happen and check that those happen, right? So you don't really need to understand what every level of the code says here, but you see the same basic elements: setup, interactions, and then a test oracle that checks the result, right? Here we have a test of a RESTful app through Postman. And this has a GUI where you state the kind of request, which is our input, right? So what we're going to do here is that we are performing a GET request in this particular URL, right? So we send the GET request to this endpoint, right? And that's our input. Then the test body is going to contain our oracle down here, right? And our oracles, that's our expectation on the result. Well, what should happen? Well, it should not be an error. It should return basically the status 200, right? Which means the normal execution. 200 means there's no error. We want it to have an empty JSON body. So here's a slightly more complicated one on the right. We want it to not be an error. We want it to have an empty JSON body, and we want it not to have the JSON body that says error. All right, so this is one oracle. This is a different oracle. This one says status 200. This one's a little more complicated. We have basically the equivalent of some assertions. And again, you don't need to memorize this. You don't need to be an expert on this. I'm not going to ask you to write tests in Postman or anything. But what I want you to see here is that all of these different testing formats have the same common elements: input, test steps, oracle, setup, and teardown. What differs is how you interact and what kind of interface you're working with. So why all this focus on system level testing here, on testing through an interface rather than the low level pieces of code? The reason for this is because when we focus on variability, that's something that we tend to implement at the system level, where we make those choices between different entire blocks of the system that we might be substituting in, rather than the single unit. When we discuss features and options, those features are not how we interact with those features is not necessarily by calling a single method, right? We don't necessarily implement variants within one class. I mean, you can, but not necessarily. We might swap classes. We might swap entire subsystems when we make those substitutions from the product portfolio. We can still test here at the unit level, and we do, right? We unit test extensively as part of domain engineering on the individual artifacts that we're building as part of our product portfolio, right? And we'll definitely test those reusable assets in isolation, but product lines introduce incredible complexity in the systems, and many of the particular errors that you can see are because of the high-level choices we made, the product configuration we made to produce a variant. Right? And so many of the errors we see emerge in the interactions between the different features and the particular options we chose for the full application. And so we have to do extensive system level testing as part of application engineering, as part of building a concrete product. This is not something discussed as much in maybe your earlier testing classes, where I imagine you focused a lot more on unit testing. But here we need to look at how the units and how the entire subsystems interact with each other when we introduce variants, and how and which elements need to interact at runtime. Are there any questions so far? All right. Then let's talk then about how we create system level test cases. And so really creating system level test cases is a 5-stage process, where first you need to figure out what the independently testable functionality of your system, or if you're testing at the subsystem level, of what your subsystem is. What features or functions are surfaced by an interface and can be tested relatively on its own outside of other high-level functionality of your system? What can we push and observe in the software? For each of those pieces of functionality, what is it that varies? What are the choices we make when we go to run the system, or when we go to execute that functionality? What do you have control of when you test? This includes both your actual input parameters, like what you pass into that functionality. It also includes any other choices you make when you test. In the product line, that includes your configuration as it relates to that functionality. What are the features you chose, or the options you chose for that functionality? And in addition, this can also be anything else that you have control of when you're testing. For example, and that might include things like your networking or control environment. That might include the hardware configuration of the system you're testing on. That might include the contents of a database you connect to, right? But at a high level, anything you control when you are going to test. Then for each of those choices, then what are some different types of input or different types of choice of options that you choose for when you make that choice, right? What kind of input can you apply that triggers different outcomes of that functionality? You then combine the choices you make, right? The options you choose for each of those choices, and to form abstract test case specifications. So at a high level, what kind of test could we write based on combinations of those choices? And then you can create from those concrete test cases, where rather than saying a positive integer greater than 2, you might put in 5, right? Where you go from abstract descriptions of test cases to the actual test cases you run on the system. So let's go through each part of this. So first of all, we have these independently testable features. An independently testable feature is some kind of well-defined function that can be tested in relative isolation from all the other functionality. This is often pretty clear when you're looking at system level testing, especially. You look for those verbs, you look for those actions that you can perform with the software. If you're working with an interface, right, this is generally then whatever kinds of functions you can access through that interface. So if our target is a subsystem, and even if we can access its underlying classes, we don't target those classes. We did that in unit testing already. What we look at is how those classes come together and what kind of jobs that they can perform. We look to the interface, and we see what it tells us we can do. that can be much fuzzier in a GUI. We're testing end-to-end journeys when we're testing end-to-end journeys from user perspective. There you want to look at the use cases, user stories if you have those, that illustrate different paths through the system and different kinds of basic functionality that you might access independently from other kinds of functionality. Right? In general, though, for a user interface, it's what the user would see as a distinct independent function. For example, if you are posting on a web-based message board, well, one thing you might be able to do is bring up a list of members. That's an independently testable function of that system, right? We click a button and it brings up a list of all the members. Now, when it brings up that list, it sorts those into alphabetical order. So when we're testing this site from the system level, list members is an independently testable function of the software. We can try that out. We can make sure it gives you the right outcome. It's accessible through the interface. But on the other hand, the sorting of the member list, when we click this button, it brings up the list. It's sorted in alphabetical order. The sorting is not an independently testable function because we don't click a button that says sort. It's something that's done on the lower level, and so we don't care about that. But we do care about whether we bring up the member list and whether that is the correct member list. Registering for this forum, that would be another independently testable function. You can fill out the provided form and see if your account is created, right? So executable tests, as I mentioned, are often written in terms of units of the code. So when we're unit testing, we look at individual classes generally. But independently testable functions are more capabilities of the software. They don't correspond as cleanly to single sections of the code, but rather cross-cut throughout the entire code base. Right? They may not even correspond to one separate unit or one separate subsystem on their own. That may be the combined interactions between several subsystems that work to bring you these independently testable functions. Right? As I said, these are usually verbs. What does the software do? What can you accomplish using it? What actions can you perform interacting with the software? These may not correspond to individual units, but like I said, large chunks of code, right? And really, this is what we're looking for, is this definition of an interface. And that's what the purpose of an interface is to define what the system can do, right? So look to the interfaces and look to what those tell you that you can do interacting with the software. And those are really your independently testable functions. Try and look at this from the outside. Try and pretend it's a black box where you don't know what the code is underlying it. You just know that what actions you can perform using it. Right? And so those capabilities we know the software will have, those are the things that we focus on in system level testing. So the outcome of a function depends on the choices we make when we test it. And then what do I mean by choices then? Well, that's anything we have control of when we test. The parameters, the choices for each of the features or feature configuration, and the environmental factors that can influence the execution of that function, right? So the obvious thing here, the input parameters of the functionality. We often provide input or provide information to the system. It acts on that information and it gives us a result back, right? So those are things we have control on of when we test, is what kind of information we provide to the system for its parameters. And we choose values for those. However, as we know, explicitly defined parameters might not be the only thing that determines the outcome you get from a function. So in a software product line, we also choose our feature configuration. We make choices for those different variation points. Which choices did we make, right? Those are also choices we make when we're testing as well, and will influence the outcome of executing the system. And then third, what other environmental factors could lead to a different outcome? There can be many of those. These are implicit parameters, and they can have a big impact in the outcome of executing that function. So things like your network connection, how many concurrent users are accessing this system? Does a file exist or not? What is in that file? Can you connect to a database? What is the contents of that database? Does it already have the record we want to insert? Is the hard disk full? Those are all choices that could impact the outcome of executing a function. And we might want to consider some of those when we're testing explicitly, because those are things that could affect the user's experience in using your app. So we want to consider any important factors that could change the outcome of working with that function. So let's say we have this user registration feature on the website. What choices do we make? Right? So we have an independently testable piece of functionality here, which is registering. When we're registering, what kind of information can we provide to that, and what can we control when we're testing? Well, first of all, what are the direct inputs asked for in that feature? It asks for a first name, a last name, maybe a date of birth, an email address, maybe a password, maybe a short bio, right? So that's all things we can try and fill in different outcomes for, or different types of values for, and see what happens, right? Those are all choices we make when we're testing. What first name do we enter? What last name do we enter? What date of birth do we enter? What email address do we enter? Okay. Now, the explicitly defined parameters might not be the only ones you want to deal with. So if you're registering users, what else can influence the outcome? Well, maybe we have our website is part of a product line with different database options. And so then we choose a database type as part of the feature configuration. So that's a choice we make when we're testing. And then we have these implicit environmental factors that can influence the outcome of execution. Right? How we interact with this database can influence execution. And so there's choices we can make when we're testing that have to do with that database. For instance, are we connected to the database successfully or not? And then does the user already exist in the database? Because that will give you a different outcome than registering a user that isn't already there. So these are more choices we can consider when we're testing, right? And you want to think a little about this. You may not concern yourself with every one of these possible, because that can balloon the number of test cases pretty rapidly. But some of those might be important to try out because they might be a concern we have in practice. For instance, we should probably write a test case where the user's already in the database just to see what happens, right? And so we take these into account. That means for this particular functionality, register for the website, we're making 7 choices when we test. First name, last name, date of birth, email, database type, database connection, whether it's there or not, and then is the user already in that database? So 7 choices when we test. Now, the key to identifying more choices is in understanding how the input parameters are being used by the functionality. For instance, you might want to know the data type. The data type is pretty useful. Like, you know, the first name is a string and that the database contains user record structures. That can be useful for understanding how that input's being used and then feeding in things like malformed input. But then any context is also useful for how those are used in practice and how they can impact execution. If the database already contains an entry for that combination of fields, maybe we know that registrations should be rejected, right? And then we also know that we should reject the registration if the database is full or if the connection is down. And so we can consider then how the choices we make are going to influence the expected outcome and check that expected outcome is met. An input for a function might then be split into multiple choices based on our contextual use. The database is something that exists, but database isn't the choice. It's how we use that database, whether it contains a record for the user, whether we're connected to it, maybe what the size of that database is and whether it's full or not, right? Those are ways we'd split one concrete item, the database, into different choices we make and consider when we're testing. And those choices will influence what we set is the contents of that database or whether we're connected to it, right? So just to think a little bit, we might have a class registration system. And when we think about a system, something like that where we go and register for courses, we could think about, well, what are some of the independently testable functions of this system? And if we think about some of the options might be things like registering for a class, dropping a class, maybe we want to transfer credits from another university, or maybe we want to apply for a degree, like similar to what you do in something like LADOC, right? So those are different type independently testable functions, things that as a user we can access through an interface, and we can make sure that they work by providing different test input. If we choose one of these, registering for a class, what are the choices we make when we're testing? Well, they might be things like, what is the course number we want to register for? That might include the contents of your student record. Have you taken the course before? Right? We could split this down quite a bit. Have you taken the course before? Um, have we passed the prerequisites and so on? Maybe there's a course database, right? So where you can check and make sure that we're registering for a real course. Maybe maybe we need to consider the contents of the student record database to make sure we can retrieve the record for that student, right? That student record is something that where we look at this and we need to look at how it's being used, because it's not one input choice. It's rather a number of choices when we're testing. Like I mentioned, things like, have you already taken the course? Do you meet the prerequisites? What university are you registered at? Can you take classes at the university the course is being offered at? Those are all things that might influence the outcome of the execution of that test case. All right, so there's a number of choices we might want to make, and possibly even more. You can see how this gets complicated quickly. If this doesn't matter, you can kind of ignore it. If it's something that you might want to try once, you might try it once and not in combination with other elements. All right, but you might want to consider these things because they can influence the outcome of the functionality you're working with. For registering for a class, right? So what course do we want to add? Is it a real course? Can we access your student record? Have you already taken that course? Are you registered at the right university to take this course? Can your record be retrieved from the database? Does the course itself, oh, I had it twice. Does the course exist? Does the student meet the prerequisites for it? And so on. Are there any questions so far? All right, if you have any, please throw them in the chat. But what we're going to do is we're going to go ahead and take a break. Let's come back at 2:20 and we will continue from there. All right, let's go ahead and resume. And as usual, if there's any questions, please send them to the chat. Right. So our next step then is to identify the representative values, right? So we know the independently testable functions. We know what choices we make and we're going to test. The next thing to do is identify what the options are for those choices. And those are our representative values. That's the input we're going to provide to the system for those choices. So if we want to test the software, we need to provide input and we need to choose between the values that are available for those choices. And for some, that's pretty easy, right? We had a bunch of yes, no choices in that example a couple of slides back for the class registration system. Does the student meet the prerequisites, yes or no, right? Can we access the student record database? Yes or no. Does the course exist? Yes or no, right? For most cases, though, we don't have exactly two options. What if the input is a number, right? Or for the input of which course to sign up for, we might have many, many different course options. If we're choosing between the options for a feature configuration, where you might have 8 or 9 different options realistically. So what values should we pass in? Well, maybe we should try everything, right? Try every course, try every possible input. Well, okay, maybe not, right? So if we just take a simple calculator and we just look at addition and we just restrict the numbers to 32-bit integers, and if we want to try every possible option when testing that, how long would that take? How many inputs are we talking about, right? Well, okay, so you have 2 to the 32 possible integer values for every parameter. And we have 2 inputs, A and B, so that's 2 to the 64 options, or 10 to the 13 test cases. All right, that feels like a pretty high number, right? How long would that take time-wise? Well, if we're generous here and we say we can run a test per nanosecond, that works out to about 10 to the 5 tests per second, or 10 to the 10 seconds overall. Doesn't sound too bad, but that's about 600 years, right? And that's for something as simple as the addition of 2 integers. So obviously, we're not going to try every possible input value that you could apply. We need to instead break this down a little bit and try different kinds of input values. So as I said, we can't exhaustively test in the real program, but you don't really have to. The fact is that not all inputs are as useful as others, purely from a verification perspective. There's only so many outcomes of a function, and you're going to have a lot of inputs that lead to the same outcomes. Why not use all of them? Or sorry, why use all of them, right? Well, we can cut that down. So fundamentally, testing is something we do to try and find problems, right? And some inputs are going to be better than others at revealing those problems. We want those ones. We don't know what those are ahead of time. But as a start, we know that 2 tests with inputs that are very different from each other are more likely to reveal faults than 2 tests with very similar input. Maybe we have a method that takes in a text buffer and breaks it into lines of 60 characters each and prints those to the screen. Well, maybe we've created 2 tests so far, and one is a 40-character string and one is a 30-character string. And now we want to choose a 3rd test case. And for our final one, maybe we would choose a 100-character string. We don't know that the 100-character string is a better test case, but we would be more suspicious of a set of tests that was biased toward lengths of less than 60, that point where we break a string into multiple lines when printing to the screen. So as a start, that's great. We want to cover a wider range of the input space. Try something that's very different from what you've already tried. You're more likely to hit a different outcome of a function, or some weird corner case that's likely to break the whole thing, right? So that's a simple but important lesson. Try things that are very different than other things. So we don't want to test exhaustively, but we do want to hit a good span of that input space. So the next thought might be to just choose a random sampling of inputs. Consider all inputs equal and try different ones. On one hand, that's great because that avoids bias. We can't say we're blind to their software's potential limitations. It allows automation. I mean, we could just try random input and see what happens. If it's cheap to run tests, that might be a viable strategy. Just keep trying until we uncover all the bugs or we run out of time. And that can be useful. There are some semi-random automation approaches that are quite effective, and I'll actually talk about fuzzing on next Tuesday, and talk about how you would automatically generate test input using a semi-random strategy, and that can be quite useful. But if we're designing tests by hand, and even automated approaches aren't completely random, random testing is not necessarily useful because you're basically hoping to get lucky. Even if you generate thousands of random tests, you've likely only covered a tiny subset of the possible inputs we can apply, and we might be repeating work. We have no guarantee we've chosen very different inputs, and you might have hundreds clustered in a very small corner of that space. So when we're designing tests, what are the things we should keep in mind when choosing the different types of input values that we'll try for the different choices we can make? Well, the next step is to take a good long look at the input space for each of your variables, each of your choices. This is the space of all possible values we could choose for a variable. And in truth, faults are pretty sparse in this input space as a whole. But they're dense in the part of the input space in which they appear. If we try an input that hits this space, we're likely to hit a fault. Or over here, we're likely to hit a fault. But if we're here, or here, or here, or here, we're not going to, right? So if we try an input and it fails, there's a good chance the highly similar input will also fail. And if we try something that succeeds and something similar to that, there's a good chance it will also succeed, right? In practice, though, you can almost always divide this input space into partitions, into logical groups of inputs based on some criteria, maybe based on the different outcome they'll trigger. And the thing is, if we do a good job of partitioning and then we try input from each of those spaces, we're more likely to come up with an input that lands in a space that's dense with faults. It goes back to something I've touched on just a second ago. A key idea here. As a general strategy, we should favor different inputs over similar input. Try two very different things, and you're more likely to trigger a fault than trying two very similar things. Even more so that if we put some thought into where those inputs come from, if we systematically go through and try a few inputs from each of those partitions, we're more likely to hit a larger range of different results than just randomly trying input. If a feature can result in different outcomes, we're more likely to hit all of those by breaking the input space down along different lines. And as a result, we're much more likely to hit the space where the faults are dense and trigger a few of those. So by incorporating domain knowledge and experience, you can make sure the tests actually do cover a representative portion of the input space. So by partitioning the input domain, we can then form a set of what we call equivalence classes. These are portions of the input space with input that's essentially interchangeable. An equivalence class of tests of options essentially tests the same scenario. They give you the same outcome. They trigger the same behavioral pattern, the same usage of a feature. They do the same thing according to some criteria that we've come up with, right? So the inputs from the group are interchangeable. We can swap one for the other, and this isn't always, that not necessarily true, but in theory, they'll give you the same outcome. Right, and if one input reveals a fault from that equivalence class, then others will probably do so as well. And likewise, if one does not reveal a fault, then others probably will not either. Perfect partitioning, perfect choices of where to divide those lines is hard, but we try our best with a combination of intuition, experience, and some common sense. Right? So if you think about it, if you have a substring function, it takes in a string and an index and returns everything after that index, or everything up to that index. What are some ways we could divide up the string and the index? Right? Well, we might want it as just a default option. Try different values of that index. Try something that's negative, because that should give you, that should maybe give you nothing back, right? Try something that's zero, that boundary point. Try something positive. Have a string with a length less than the index or greater than the index or equal to the index, right? Those are just some things that might come immediately to mind. And these hint at some strategies for how you can divide up this input space, right? So a few things you can do is that you can look at equivalent output events, see if you can group input values based on the outcomes they trigger. You can look for ranges in numbers or values. What are some different discrete ranges of input values that can be provided that might give us different outcomes based on the context they're used in? You can look for membership in some kind of logical group. Can we group these inputs based on how they're used, what kind of context the method uses them in? Do members of this group trigger similar behavior? You can look for time-dependent input. Does the timing matter? And is that something you can consider? You can look at the operating environment and how that can influence the system behavior, the hardware choices you make, or the networking environment you operate within. Certain data structures, such as arrays, are often broken down into common groupings of input. And then remember to look at the boundaries between these partitions as well, because that's where a lot tends to go wrong. So first of all, is start from the output, divide the output into the different outcomes that you can get for this feature we're testing, and then work back to the inputs and see if there's a logical mapping of those inputs to particular outputs they come up with. This is your general first step in here in how you'd break down the input into different types of input you can apply. And we often then break down further from there. It's often easier to find good tests by looking at the outputs and then working backwards. So for example, we might have a piece of functionality that gets the status of an employee based on the employee ID. And we know from this, there's different types of statuses. There's a manager, there's a developer, a marketer, a lawyer, or maybe outcomes for like the employee doesn't exist, or there's a malformed ID. And so those in turn suggest different options you can choose for the employee ID. You would choose from the set of managers and expect that you get manager back. An input from the set of developers is likely to give you a developer back. All right, and so on. These suggest different abstract values for that choice of employee ID. And then in turn, you might break these down even further. When you're dividing input into different input partitions, it's natural to look for how you could split the values of the inputs into discrete ranges. So divide based on its data type and how the variable is being used. So for example, any value from a particular input range should have a similar effect. And so maybe you have an integer input, and you know it's intended to be used as a 5-digit integer. It's maybe a postal code, right? Between 10,000 and 99,999. Now, okay, so that suggests in turn some things we should try, right? First, we might break this down into something smaller than 5 digits, because that should not work. If this is a system intended to work with postal codes, and postal codes are 5-digit, something that's 4-digit should trigger an error. So let's try something from that. We have our normal 5-digit range, 10,000 to 99,999. And then we have things greater than or equal to 100,000. So 6 digits or above should also not work, right? And so you'd at least try those 3 different things. And if you think a little more about other special numbers that might do something weird, you might try those as well. For instance, we might try something negative, because that, what if you enter a negative 5-digit number? Well, that shouldn't quite work either, because that should, you don't expect a minus sign in your postal code. Maybe you should try something that's exactly 0. Sometimes weird things happen there. Maybe you try the maximum value integer, because maybe that's something that's going to cause an overrun because we handled something incorrectly. We added a 1 somewhere, right? And it would break then. So just try some weird things. Can you pass in something that's non-numeric, right? Does this, for some reason take a string and you could pass in someone's name and break it? Try that. Could you pass a null value? Try that, right? In general, you want to hit a typical value, something from your expected range, and then hit each of the cases at least once to fall outside of your expected range. And consider the weird corner cases that may be likely to trigger issues. Right? You might want to look for how you could break down the input into logical groupings. And here again, it's some context behind how a program uses that input. Often you have different logical groups in mind when you come up with a feature, and so you try inputs from each of those logical groupings. So for example, maybe you have a program that takes in a country name and a floor layout. And those are things that can be broken down into logical groupings. Maybe you're looking at like different real estate layouts. And so you have an apartment versus a business. Those are different floor layouts you could try breaking down into. Country names, maybe regional, you have different regional expectations. So, one's for Europe, one's for Asia, one's for South America, and et cetera. And try those out. And then often those groupings are quite broad and we can break them into smaller subgroupings, break them down into apartment types, right? Or, UK versus Germany, or I don't know, something. Depends on the needs of your program. The idea, though, is you can look at how variables used and break into logical groupings based on what it represents within your program. Look very hard at timing. The timing and duration of input are often as important as the value you pass into that input. Make sure you consider those timing as well. Timing is very hard. It's very crucial to get right, but it's also something that can be really, really important. And for many systems, the timing of an input is an implicit input in itself. It's a choice you need to make. So if timing matters, you need to remember that it is part of your input and then partition that accordingly. For example, if you consider a pacemaker, it's an implanted medical device that tries to ensure that the heart beats at a regular rhythm. The pacemaker is reading electrical impulses that represent your heartbeat. And if it doesn't see one within the right timing window, it will then shock your heart to try and get things back into regular rhythm. Right. And so what you might do is see if you can trigger an electrical pulse at a certain point before a deadline as input, right? Provide a pulse in 1 millisecond before that deadline, exactly at your deadline, and 1 millisecond after your deadline, right? And then see if your program reacts accordingly. See what kind of boundaries it has built into this. Strange behavior can often happen maybe when you're reading from a file or writing to a file. And then so you could try things like closing the program or closing or causing a disruption before, during, or after writing to or reading from the disk and see what happens. In any case, timing is something that is often important and can also be partitioned into different options. Similar to timing, you might want to consider the environment the program operates within, as that can easily impact the behavior of the program. So the environment is also something to consider when you're forming value partitions. Consider the environment you're operating in, how it can influence the input or output of the system, and how the combination of both explicit program input and implicit environmental variation can be partitioned. Memory can cause problems. Well, if you don't have enough memory, what if you have enough physical memory but not enough free virtual memory, and so on. Same for processor speed or architecture, right? You could see deadlock between processes, unexpected slowdown, race conditions. In general, try using different hardware specifications from time to time if that's something that's important and can affect the results of the system execution in a way that can really harm the user's perception of it. You could try to do things like vary your processor speed, memory, and disk capacity. Look at your networking environment. Your client server environment can have a huge impact on the operation of your system. So you could try with different numbers of concurrent connections to a client. No current connections, some, a lot to try and trigger denial of service conditions. Look at your network latency. You could vary the types of the virtual network environment you're testing within, right, and so on. Consider different communication protocols, SSH versus HTTP versus HTTPS, if those are options you can choose from, if those can affect your program in some way as well. Certain data structures are prone to particular types of errors. This is especially true if you're looking at things like C and you're looking at pointers, as those are just rife with errors. But, maybe consider things like arrays or list structures, right? And you might want to try a list or an array with only a single value in it. You usually think of an array being passed into something that's going to have many different values, right? So it's common to embed that assumption into a program. And so if presented with a single valued sequence, your program might fail, right? You want to try that. Try with various sizes of the array and then various numbers of items stored in there. it decreases the chance the bad program will accidentally give you a good output because of a particular input choice you made. You can see if you have issues with particularly large arrays, things like that. Look at the ordering of elements too when you're passing those in, and make sure you're accessing different elements of the array. Maybe you could see if at times behavior might differ if the element you're looking for is at the beginning or end or middle, if you're doing like a search, for instance. So you try different locations where you're storing the element of interest. Let's see. So we can take a look again and just another example. And here we have a max method that takes in two integers and returns whatever the largest of those two is, right? So dead simple. And we can think a little about what we would do if we are going to test this. How would you break down these inputs into different representative values? And so we have these two integers, and we can, of course, consider them in isolation. Try a negative value for A, a positive value, try 0, same for B. But also you would consider how those variables interact with each other and consider the combinations of them that can change the outcome, right? Try something with A larger than B, with B larger than A, and something where they're equal, right? So you consider not just the inputs on their own, but also how they interact with each other, and then choose values that can take advantage of that interaction, right? And make sure that interaction works as you would expect. So here's where we are so far. For each of these independently testable pieces of functionality surfaced by the interface we're testing through, what we want to do is we want to identify the choices we make when we're testing that. And then for each of those choices, we identify the representative values for that choice, right? Chop up the input space, the different partitions. So now we have each individual choice partitioned. For tests then, to create a test for a system, we don't just feed one item at a time, we feed in the full set of input. And so what we do now is we combine these different, the representative values choices we can make for the different variables together and form then what we call a test specification. A test specification is an abstract recipe for a test case. It says you're going to fill in this type of input, right? And then for each of those abstract test recipes, you can then instantiate one or more concrete test cases by providing the actual values we're going to pass into the program that match those partitions that we chose. Does this make sense? Again, feel free to ask questions if you have any. Right? So in coming up with the equivalence partitions for our choices, we need to think about what exemplifies that space of input values. And you want to make sure you hit the types of input that can be passed in. So here we have something where we're going to insert a postal code into a list. It takes in an integer representing that postal code, and it takes in the list it's going to insert it into. All right, so then if we have this integer and we have this list, how do we break this down? Well, we saw from the example a little earlier that in this case, maybe we have this 5-digit integer. And so we want to make sure we test something that's less than 5 digits and something that's more than 5 digits to make sure that it throws those out as we'd expect, right? And then of course, test something that is 5 digits. We have a list. What within the context of our program, this is a list that can have a length of a max 10. So it's a list of at most 10 postal codes, possibly fewer in it, but 10 is the max. And so we have some possible partitions for this. We have an empty list, of course. Pass that in, make sure that adds the item accordingly. We have a list of one item in it, just to test a single item option to make sure that works. Try something between 2 to 10, maybe try something that's more than 10. If we intend this to only be in a 10 item list and we pass in something of a greater capacity, maybe we'll get the wrong answer, right? So try that. So we have these different options that we can try. So now then we have these representative values, and for a test, we want to combine these. We don't just pass in values to a single input, we pass in values to both inputs when we run the test case. So to form our test specifications, our abstract recipes, what we need to do is list out the possible combinations of input partitions for all inputs, right? So we have 3 options for the integer, we have 4 options for the list, And so we have 12 abstract specifications, right? Just the different combinations, less than 10,000 with an empty list, less than 10,000 with list of length 1, less than 10,000 of list of length 2 to 10, less than 10,000 of greater than 10, and so on, right? So 12 different abstract test specifications you can form. Now, to run those on the real system, then we create concrete test cases from these recipes, and we can have many, many different options here. But for example, for this first one, an integer of less than 10,000, so something less than 5 digits, and an empty list. Well, we have an empty list and 5,000, right? Something that's something that is a 5-digit integer and a list of length 1. It's so 96521 for the integer, and we have a single item list. Something that's greater than 5 digits in the list of length 2 to 10, 150,000, and we have 2 5-digit numbers already in that, and it should throw that out because it's 6 digits. Right, and we can create more and more of these for each of these. So however many of these we want to try, but we'll do at least one from each of these. Make sense? Okay. So we have now our set of test case specifications. We have all these abstract combinations of input types we want to try, and now we transition to concrete test cases where we feed in the actual values. This is a simple instantiation of these test specifications. There's still a few things to keep in mind though. For one, there's a reason we do both specifications and concrete cases, which is that when you feed in multiple tests with the same specification, only one of those might still trigger a fault in the code, right? And so we might want to try more than one concrete test case, especially if we can think of some options that might be a little weird and might cause a problem. And so we'll try those out. Now, no matter how you chop up those input partitions, most of the errors tend to occur at the boundaries of those divisions, where something could fall into one partition or the other based on how you coded it up. And so in choosing concrete values, often you want to try and things around the corner cases, around the partitions of those boundaries, to make sure that you're treating them accordingly, right? So again, we have this 5-digit number that's intended to be a postal code. And we want to try things in the sort of typical range, maybe 50,000, but we also want to try exactly 10,000 and exactly 99,999, the exact corners of these ranges. Because if you have like an off by 1 error in there, this should be accepted, but maybe it'll be rejected. Same here at 10,000, maybe it'll be rejected, but it should be acceptable, right? And so you want to try it out. Likewise, on the outskirts of the other partitions, anything that's 4 digits should fail, but try 9,999 because it might be allowed through, even though it shouldn't be if you have an off by 1 error in there. Or likewise, 100,000 might get accepted when it should be rejected because you have an off by 1 error, things like that. Right, so make sure that you try these corner cases as well. All right, so we're a bit low on time. We have about 10 minutes left in total. I have an activity that I would like you to try, but I don't think we really have time now. So what I'd like you to do is try this before next class. There is a worksheet linked on Canvas from the schedule page where we have the list of classes and slides and all of that. There's an activity linked. The gist of this activity is that we have a microservice related to sets, and it has 3 functions it offers, where it inserts an object into the set, it can find an object in the set, and it can delete an object from the set, right? And so what I'd like you to do is come up with abstract test specifications, those test recipes for this, using the same process we talked about, right? You have 3 independently testable functions here: insert, find, and delete. Now, for each of those, identify the choices you make when you're testing. What do you have control over? And for each of those choices, identify the representative values you can feed in for that choice, right? And then combine those to form your abstract test specifications. For each of those, I want you to state the expected program output, right? So for example, right, so we have this insertion. It takes in an object and adds it to the set. Well, what are our choices? Well, our choices might be the number of items that are already in the set and the status of that object. Is it already in the set or not, right? And so those are our choices. And for each of those, what are some values we can come up with? Well, maybe that's the object is already in the set and the object is not in the set for that object status. And for the set, maybe it's just, we choose the number of items. And you can break this down into there's 0 items in the set, there's 1 item in the set, there's 2 to 10 or something like that. So as an example of one specification you might form, you might have a set with 1 item already in it and the object's already in it. And so the expected outcome would be the object is not added, right? Like I said, there's not really time now. I recommend you go and work on it, but there are some answers in the slides. And just to give kind of a quick example, for example, for the insertion, we have it's in the set, the object is in the set already, it's not in the set, or maybe it's a null object, it's a null pointer. And for the number of items in the set, it's empty, 1 item, 2 or more items, or 100 or more items. And, it might be slow then, but we want to make sure it works. And you can come up with, for example, things like we showed that it's an empty set with the objects not in it, and so the object should be added. It's an object with 1 element, and it's not in it should be added, and so on. So here's a subset of them. Try the activity, check the answers, make sure this process makes sense. And between now and next class, try that out. And if you have any questions, you can email them, you can ask on Canvas, or you can ask in the chat next class. Right? Just to make sure you understand how this process works. So to summarize, unit testing is centered around a single class, whereas system level testing is centered around testing through an interface and testing how we can bring those low level elements of your system together to form the complete functionality. To come up with system level test cases, you identify the functionality that you can access through that interface and test in isolation from the other functions. For each of those independently testable functions, you identify the choices you make when you're testing. What do you have control over, and what can affect the outcome of the function you're working with? For each of those choices, you cut it down into a set of representative values that can trigger the different outcomes. They can influence how that function executes. And then you combine those choice values to form test recipes, these test specifications, and then fill in concrete values for those choices and run those against the system and see what happens, see if you find any bugs. Next time, we're going to talk more about this and how you can try and test important and identify important feature interactions and focus on those, because often this process leaves you with more test cases than you would actually write and run. And so we need to break this down some more and to identify the important items to test. And so we'll talk about 2 methods for doing so next class, based around either trying to prune back the number of options by adding constraints, or in trying to choose a nice small subset just to cover an important range of these. That's all I have for the class today. The assignment's due tomorrow, so make sure you're working on that. If you have any questions on what we talked about, or if we have any questions on the assignment, feel free to ask them, and I'll hang out for a few minutes in case people have any questions. Otherwise, I will see you on Thursday, and we'll talk some more about system level testing and choosing important feature interactions. All right, there's a question if there's an ideal ratio of how much time that should be spent on testing. Not in total. It really depends on the complexity of your project. Testing in many cases actually accounts for as much as 50% of your development time on a complex project. But I mean, the general thing you run into is that you have to release the software, and you're generally not completely done with testing because you can keep trying things forever. So many projects, like I said, spend about 50% of their development effort on testing, and that's not that unusual. Within that, there's often this split of like maybe 70% unit testing. It's very heavily weighted toward unit testing. And then you get into these complex system level test cases as maybe the remaining, somewhere between the remaining 20, 25 to 30% of those. And you might have some additional user-based like alpha and beta testing as well in there. Did that answer your question? Cool. Any other questions that people have? All right, then I will stop the recording and feel free to follow up next class or on Canvas if you think of anything else.